Waterproof is a web-based tool that allows for the generation of portfolios of nature-based solutions easily and quickly. Additionally, Waterproof estimates the return on investment associated with the nature-based solutions it suggests. To perform these analyses, Waterproof incorporates a series of mathematical models that have been developed in the Stanford University Natural Capital program. Next, we will review some basic concepts such as: what is a model? What is the modeling protocol? Later, we will see which models Waterproof integrates and how they were validated for worldwide use. A model can be defined as a simplified representation of a phenomenon or a process. It is typically characterized by a set of variables and by equations that describe the relationship between these variables. This definition suggests that every model is composed of three elements: inputs, outputs, and the mathematical structure. The first two elements represent the external influence on the system, in the form of mass and energy flow, and the system's response to them. The mathematical structure is the operator responsible for transforming, from a numerical point of view, the inputs into outputs. The modeling process is carried out following the modeling protocol. A modeling protocol, at its simplest level, can be divided into model identification and model evaluation parts. The model identification part mainly focuses on identifying appropriate parameters, one set or many parameter sets if uncertainty in the identification process is considered, while the latter focuses on understanding the behavior and performance of the model. For Waterproof, the group of models selected corresponds to Invest and Rios. These models were implemented for the entire Earth, using information from different biophysical variables from different global data sources that have been reviewed and validated by peer evaluators. In addition, following the modeling protocol, a parametric coherence analysis was performed on the models to ensure that the orders of magnitude of the simulated variables were consistent across different continents. Waterproof uses Rios and Invest to answer the questions of what nature-based solutions should be implemented and what benefits would these nature-based solutions provide in terms of water quantity and quality. With Rios, Waterproof addresses the first question, while with Invest, it addresses the second. The following diagram presents the conceptualized analysis flow for Waterproof. As can be seen, the Invest models are run in a first stage to estimate the water quantity and quality conditions at a previously defined water intake point. With this information, Waterproof suggests to the user which drinking water treatment plant to use. In the second stage, when the user has configured the entire case study, Waterproof runs Rios to obtain a spatial portfolio of nature-based solutions, taking into account the nature-based solutions that have been defined by the user. Then, Waterproof runs the Invest models for the business as usual scenario and then for the nature-based solution scenario. It is important to note that Waterproof runs Invest in the nature-based solution scenario for the number of years of implementation that the user has defined in the case study configuration. For example, if the user assigns that the implementation period of nature-based solutions is 3 years, Waterproof will run the Invest models 3 times, using the coverage information that results from the 3 portfolios generated by Rios. In the end, with the information from the models in each scenario, Waterproof estimates the water quantity and quality conditions for each scenario and then estimates the difference between the scenarios, which would correspond to the portfolio benefit. The prioritization logic behind Rios involves the possibility of carrying out a series of activities in a watershed which somehow generate changes in the landscape or transition. Among the transitions that can be made are: keep native vegetation, protection. This transition focuses on conserving native vegetation that would likely be lost, protecting existing habitat. Revegetation unassisted. This transition refers to the revitalization of vegetation on degraded or bare lands, without active interventions. Revegetation assisted. This transition represents the revitalization of vegetation on degraded or bare lands through active interventions. Agricultural vegetation management. This transition represents increases in the structure, coverage and/or diversity of crops. Ditching. This transition consists of improving water infiltration and reducing the transport of sediment and nutrients in agricultural or degraded lands. Fertilizer management. This transition is related to any activity that changes the way of applying fertilizers in crops or pastures. Pasture management. This transition reflects changes in the management practices of pastures or natural meadows, such as the change from continuous use of the pasture entire area to division into small grazing paddocks with an intensive use of each one. This in a short period of time. Operationally, RIOS is divided into two parts. One where it performs the identification of investment portfolios and another where it generates changes at the coverage level generated by said portfolio. In the portfolio generation module, RIOS performs a series of weightings on the biotic parameters to know the influence of each process on the overall score that a pixel receives. Then assigns a score to each pixel for each transition, objective combination, indicating how large the impact of each transition on each objective in that pixel could be. In total, RIOS integrates 7 objectives, namely: erosion control for drinking water quality, erosion control for reservoir maintenance, nutrient retention, nitrogen and phosphorus, flood mitigation, groundwater recharge enhancement, dry season baseflow, biodiversity. Subsequently, it combines the scores of all objectives through each transition to create a map of the capacity of each transition to influence all objectives through the landscape. In this way, it produces a general activity efficacy map for each activity, based on a weighted average of the transition scores, as the average of all transitions that a given activity can cause. Each map suggests the probability of achieving the highest returns on all objectives of that activity. Finally, the activity scores are divided by the user specified cost of that activity to create cost effectiveness index scores. These scores are what RIOS uses in the portfolio selection process to decide which activities should be selected, starting with the highest score. The Portfolio Translator module allows generating scenarios that reflect the future state of the watershed if the portfolio were implemented. This module uses the portfolios to develop 2 scenario maps of soil cover and the associated biophysical parameter tables required to run the sediment and water yield models of INVEST. INVEST is a family of tools for quantifying the values of natural capital in clear, credible, and practical ways. INVEST enables decision makers to quantify the importance of natural capital, to assess the trade-offs associated with alternative choices, and to integrate conservation and human development. The interesting thing about INVEST models is that they have low information requirements compared to more complex tools, but still, these models can identify areas where investment can improve human well-being and nature. Currently, Waterproof integrates the following INVEST models to evaluate the benefits of nature-based solutions, namely: annual water yield, seasonal water yield, sediment delivery ratio, nutrient delivery ratio, carbon storage and sequestration. In the development of Waterproof, for the aforementioned models, a parametric consistency analysis was carried out using Monte Carlo simulations. The INVEST models incorporated in Waterproof are spatially distributed and temporally aggregated, representing annual averages. The models receive inputs in raster, vector, and text formats, corresponding to the physical variables necessary for modeling. For example, digital elevation model, basin, and biophysical table, and the parameters specific to the models. In addition, the model can generate aggregations in a specific area, for example, in basins, for which it uses vector files. Internally, each model has a mathematical structure that allows it to represent the variables of interest, such as water yield or annual sediment export. All calculations performed by the INVEST models are pixel by pixel, so most of the model outputs are of the raster type. However, the models can perform aggregations at the basin level. Some models, such as annual water yield, also generate outputs in text format for ease of handling. The annual water yield model allows for estimating the relative water contributions from different parts of a landscape, providing information on how changes in land use patterns affect the annual surface water yield. It is based on the Boudico curve, which considers variables such as annual average precipitation, annual reference evapotranspiration, available water content for plants, and soil depth. The model only has one parameter, the seasonality factor, which represents the hydrogeological characteristics and seasonal distribution of precipitation. The main output of the model used by Waterproof is the annual water yield, but the model also produces variables such as average actual evapotranspiration. The Invest seasonal water yield model allows for estimating the contribution of land parcels to both base flow and quick flow generation. The model calculates spatial indices that quantify the relative contribution of a land parcel to both base flow and quick flow generation. Procedurally, the model first estimates quick flow using a curve number-based approach. Then, using quick flow, precipitation, and actual evapotranspiration, it calculates local recharge or potential contribution to base flow from a water balance. With this last variable, the model estimates base flow as the average of contributing, positive or negative, local recharge in the basin. The seasonal water yield presents three parameters to represent this process. 1. The proportion of available annual upward recharge that is available in each month. 2. The proportion of upward gradient subsidy that is available for downward gradient evapotranspiration. 3. The proportion of available local recharge for degraded pixels. The main output of the model and used by Waterproof is base flow. However, the model also outputs variables such as monthly average actual evapotranspiration, quick flow, local recharge, among others. The sediment delivery ratio allows for quantifying and mapping the generation of terrestrial sediments and their delivery to streams. This model focuses solely on surface erosion and does not model erosion in channels, banks, or masses. Operationally, the model calculates the annual soil loss using the revised universal soil loss equation. It then estimates the sediment delivery ratio using the sediment connectivity index or the sediment delivery ratio. Finally, sediment export is given by the product of these two variables. The sediment delivery ratio has three parameters to represent sediment export. 1. The Borselli K parameter. 2. The Borselli IC0 parameter. 3. The maximum the sediment delivery ratio value that a pixel can have. The results of the model include the sediment load delivered to streams on an annual timescale, as well as the amount of sediment eroded in the basin and retained by vegetation and topographic features. The nutrient delivery ratio model uses a simple mass balance approach, which describes the movement of a mass of nutrients through space. This model represents the long-term and steady-state flow of nutrients through empirical relationships. Nutrient sources throughout the landscape, also known as nutrient loads, are determined based on a land-use land cover map and associated load rates. This model allows for the separation of nutrient loads into dissolved and sediment-bound parts, which will be transported through surface and subsurface flow, respectively, and will stop when they reach a stream. Like the sediment delivery ratio model, this model integrates a connectivity index to perform delivery calculations. In the end, nutrient export is calculated as the sum of contributions with this model. With this model, Waterproof simulates the export of nitrogen and phosphorus for the watershed defined by the user. The nutrient delivery ratio incorporates three parameters to represent the export of each nutrient, 3 for nitrogen and 3 for phosphorus. 1. Borselli K parameter. 2. Subsurface critical length. 3. Subsurface maximum retention efficiency. The model results include two rasters that show how much phosphorus and nitrogen from each pixel ultimately reaches the stream through surface flow. The carbon storage model allows for representation of carbon storage in above-ground biomass, below-ground biomass, soil, and dead organic matter. This model adds the amount of carbon stored in these deposits according to the land use maps and classifications provided by the user. Operatively, the model uses the carbon storage densities of each cover, calculates the storage, sequestration, and value, as well as aggregate totals of carbon. This model does not have associated parameters, so the representation of stored carbon depends solely on the carbon storage densities of each cover. For the parameters identified with possible ranges of variation, a simple analysis was performed to select the parameters that were most consistent with available observations. For this analysis, we used the flow, sediment, phosphorus and nitrogen data consolidated in the GEMS Glory database. A total of 923 monitoring points around the world were found in the GEMS Glory database. However, not all of them had all the information for model verification. In total, 244 points were filtered for flow, 205 points for suspended sediment concentration, 111 for nitrogen concentration, and 26 for phosphorus concentrations. For a practical working purpose for the analysis, HydroShed's Level 2 was used in waterproof for the identification of global macroareas, as presented in figure. In total, 56 macroareas of HydroShed's Level 2 were identified on the planet. For parameter sampling in the parametric consistency analysis of annual water yield, sediment delivery ratio and nutrient delivery ratio models, we used the Latin hypercube sampling method. This method is identified as the most widely used random sampling method for analysis based on Monte Carlo simulations. In this sense, within the range of variation of each parameter for each model, between 100 and 500 Monte Carlo simulations were performed with the objective of analyzing parametric consistency. The number of simulations was defined according to the execution time of the models, which in turn is a function of the size of the basins, preventing that the execution of all the simulations did not exceed a maximum time of 2 days. The mean absolute error was selected as the performance metric for the selection of the parameters that generate the greatest consistency with respect to the GEMS Glory database. The figure shows the examples of parametric consistency analysis results. Considering that the GEMS Glory database does not have data for all variables in all 56 macroareas, in order to establish the parameterization in those areas without data, a cluster exercise was performed using the k-means method. This analysis was performed for the macroareas to identify those with greater similarity, and thus consider the parameters in these areas with no data available from the database used. For the cluster analysis, 17 biophysical variables were included.